Great news, students. This is the last video lecture for this week, and this will close out Unit 4 on random variables until we move on to a few more next week. In this probability distribution discussion, we're going to talk about continuous random variables. So before we had discrete, now we're going to have the continuous ones, and we're going to see how to make the transition from one to the other and see how the rules remain the same, even though they change ever so slightly. So the first thing I would like you to do is pause the video here and try to figure out the shaded area for each of these squares. So be sure to pause the video and find out what area of these 10 by 10 squares are shaded in each of these 5 examples. On your mark, get set, go. Okay, so let's discuss. So what I'm going to say is for this first one, the 10 by 10 is a 10. And now we're going to look at some of these other ones. So for this other one, for instance, this square right here, we see one side is 10, so that must be 10 as well. And since it's a square, this whole side is 10. This is 2, so then this must be 8. So we're going to put an 8 there. That's not a very good 8. Let's erase that. And let's do a thinner drawing here. So this side, therefore, is 8. And since it's 10 by 8, oh, sorry, this is 100. Then what we have here is 10 times 8, which is 80. And this, let's just put 100. First one's easy, 10 times 10. So therefore, 8 plus 2 is 10, so this must be 8. 8 times 10 is 80. So now over here, we have a side that's 10 and a side that's 4. So that must mean that this other side up here has to be a 6. And therefore, if we take the area of 6 times 10, we will get 60. So I'm just calculating areas. Now for the next example, we have a 10 on this side, a 3 on this side, and now there are 2 more unknowns. But this one here and this one here, I will tell you, are symmetric, which means they're the same size. And with that bit of information, then we can solve this one. So this is a 3. So we have a 3 and a 3, which is 6. We're missing a 4. So this will be a 4. And that means that if we have 4 times 10, this area will be 40. Guess it really wants this to be that color instead. So let's draw again. So we have 40. Okay, so now in this next one, we have a 6, and these 2 are symmetric. So if this is 6, that leaves us with 4 for these 2. So if we have 4 for these 2, that means each of these must be a 2. So that's a 2. That's a 2. And that means that each of these areas must be 20. So this is 20. And this one is 20. So in total, these 2 together then would mean that this whole shaded area would be a total of 40. So that's just playing around with symmetry, playing around with the unknown that matches. And that is how we calculate area. Now, why do we care? Because in the case of a continuous random variable, we're looking at areas under the curve. We did it for the discrete probabilities, but it wasn't as noticeable because of a very special, unique aspect of discrete random variables, which we will talk about right next. So let me clear all my drawings and let's move on. So we are moving into this concept of probability density functions. And it's an equation used to compute probabilities of continuous random variables. So when you hear probability density function, that density means compact. And when you have continuous random variables, the possible values that exist are very compact because you can always slice it finer and finer to get an even more exact number, so to speak. So there's infinitesimal options available, which makes figuring out probability a little tricky, but a little cool. So it's still the same two properties. So if it's a probability density function, there has to be some kind of total adding up to 1, right? We know probabilities sum to 1. And if you have all of them, then there's a 100% chance that something will happen. So the total area under these graphs is also going to be 1. What's also important to note is that the height of the graph must be greater than or equal to 0 for all possible values of the random variable. So it has to be a height that isn't 0. Well, it could be 0, it can't be negative. Right, so think of when we said probabilities could be between 0 and 1. This is that same situation where we can't have negative values and we can't have really large values because then it won't sum to what we need. Now, let's review the discrete probability distribution functions we talked about last time. We'll talk about a general example we did and the binomial distribution that we did. So if you recall before, we had a probability histogram. This is for parental involvement, and the number of activities are the random variable. The probability here, if you add up that entire column, will sum to 1. And each of these rectangles here, right, has a height that matches the probability. Now, what's interesting is, remember we did that area thing above? So if we actually calculate this as an area under the curve to get the probability, what's interesting to note is since each of these values is discrete, that the bottom part of each rectangle is 1. So if you multiply 1 by the height of the histogram bar, you're just going to get the probability back. So this is why it's interesting when we shift from discrete to continuous. It's not that different. It just seems scarier because this part down here is not always going to be a distance of 1 that we're calculating to try to figure out the area. And the areas that we're going to be calculating next week aren't so boxy. So calculating the area of rectangles and squares is a very straightforward formula. When things get a little curvy, the formula starts to deteriorate when you try to calculate area. And that sort of goes into calculus. Luckily, people did the calculus for you to figure out the area under a curve with integrals and all of the really cool advanced mathematics that exists. So next week, we'll be able to utilize the generalities they came up with and the formulas in Excel to make a really complicated process very simple. If you're into visualization, this section will be for you. It's a lot about symmetry and thinking about shading in different aspects of a graph. So this is a chance to tap into your visual aspect of your brain, your artistic aspect, and utilize that to solve complex mathematics. So your chance is coming up soon. Let's look at the binomial probability distribution. Again, these probabilities are actually the area of the rectangles because every rectangle has a distance of 1 at the bottom. Since they're all separated by 1, each of these must span 1 for them to all be adjacent and touching. So it's 1 times whatever the height is, and that gives us our probability. So I've said it a few times now. Now we're actually going to have to do some area calculations to get the probability. One way to look at that is to start with a really easy continuous probability distribution function known as the uniform probability distribution. So let's get into that specific one. So if we look at the uniform probability distribution, we're going to let x be a random variable. The difference here is it's not discrete. It's going to be a continuous variable. So it goes from some value all the way through in an interval format. So when we do that, we have to come up with some kind of equation to figure out how the area is behaving for this distribution. So this looks a little scary. The y here is just going to be the vertical axis. Remember, it was the probabilities up above. And the b and a is going to be the interval that our random variable can fall between. So see how x is in the middle here? It's between a and b. It could be a, it could be b, or anything in between. And because it's continuous, it's literally anything in between. So let's move into it. We're going to look at the area under the graph of the density function to understand this better. So we're going to come up with this example for a uniform probability density function. And this one is going to be for letting x represent the arrival time of students in a class during the first 10 minutes of class. Now, it's not this class because this class is asynchronous, but bear with me. So if we're looking at the first 10 minutes of class, where 0 is on time and 10 is 10 minutes late, and those are the only things that students will do, right? Then we can set up the system where all the times are equally likely, and actually an exact time is impossible, but you can calculate intervals. So if you're trying to get exactly 1 minute, that's impossible. You can't stop the stopwatch quick enough for a continuous random variable. So that takes a little while to get used to, the fact that you can't be exact when it comes to continuous distributions, but you can do intervals by just opening them up a little bit. If you do an exact time, the width, the theoretical width of that rectangle would be 0, and it would make it non-existent. So that's why also we need intervals. Now, for the uniform distribution, the reason I start with that one is because it's fantastic to start with. It's a rectangle. And if you go from 0 to 10 in the horizontal direction, then in order for it to be a probability distribution, it needs to have an area of 1. The only way you can get an area of 1 is if the height of the rectangle is 1 over 10. So if you took 1 over 10 and multiply it by 10, it's like taking 10 divided by 10, which is 1. So that gives us all the possibilities from 0 to 10, and every single one of them would have 1 out of 10 probability. Again, you need to do an interval, though. You can't take just one snapshot. You have to span it out a little bit. But everything is equally likely with 1 over 10 probability. So this is still kind of confusing. Let's do a concrete example to clear it up. So we're going to ask the question, what is the probability of a student arriving no more than 5 minutes late? Again, with the terminology. So no more than means it doesn't go past 5. So there, 0 to 5 minutes late is our interval. So we're going to take this, there's 5 on this graph. It's in between 0 and 10, exactly in the middle. And we're going to shade up till we get to 5. Now we can calculate our probability. So the probability is simply the distance for this rectangle from 0 to 5. So 5 minus 0, which is 5. And the entire rectangle, which is 10 minus 0, which is 10. And we just simplify the fraction and we get a half. Now, does this value make sense? Well, of course it does. It's half the graph. So the probability of being in the first half of the graph is 1/2 or 50%. Now that we've done one concrete example, I think that you'd probably be a little more secure in the next ones. So I'm going to pop up a few here. What I'd like you to do is pause the video, try these out, and then when you're done, pop back onto the video. I'll get started momentarily. Okay, hopefully you've had a chance to try it out. So let's look at the probability of being less than 3 minutes late. So less than 3 minutes, again, we have to think of, we're going from 0 up to 3. So we have to be in that interval in order to be less than 3. So let's shade it in. So now that we've shaded it, we have our two rectangles. We're going to put the blue rectangle, and we're going to calculate that. And we're going to put it over the bigger rectangle. So here we have a 3 out of 10. So from 0 to 3, we have 3 out of the entire thing, which is 10. Next example, more than 8 minutes late. So that means it'll be at 8 and go bigger. Now this one's a little tricky. So here, the rectangle span for the blue one is 10 minus 8. And for the big one is 10 minus 0. So we have 2 over 10, which simplifies to 1/5. Last but not least, what is the probability of being within an interval? In this case, 3 to 8 minutes late in that middle portion of this distribution. We shade it in again, and the same game applies. We have 8 minus 3. How long is that one? And we get 5. And then we take the whole distribution, which is 10, and we get half. And that makes sense because, again, this is half the graph. In fact, remember the shading that we did early on with the square? Here we have from 3 to 8. Well, we know this side was 3 out of 10. And we know this side over here was 2 out of 10. And if we add those, that would be 5 over 10. So this also has to be 5 over 10 to give us the whole probability. I hope you enjoyed the video. That's it for continuous for now. Next week, we're going to be launching into everything to do with normal distribution. So be ready to dive in. You might want to sneak preview normal distribution, especially the empirical rule, just to get your feet wet. But I will dive into that next week. I hope you have a good weekend. Stay on top of the material, and I'll see you at the next video lecture.